Okay, this is the video for chapter 22, Gauss's Law. We're going to continue talking about electric fields, only now we're going to start to talk about what's happening at a surface and within surfaces. We'll introduce a new concept of electric flux and how to calculate it. It turns out electric flux is related to charge. It's also related to electric field, using this very important idea of Gauss's law, which is actually going to simplify our calculations of electric fields without using calculus. In the chapter 21, what we did was we said we had some charges on some distribution and it's going to produce some electric field. Really what we're doing in this chapter is we're saying, suppose we measured an electric field, can we figure out something about the charge distribution that's causing this electric field? So that's really the main difference between the two chapters. As advertised, I'll introduce a new concept of electric flux, or flux is another word for a flow, so really we're looking at the flow of electric field through some area. And what we're doing is we're saying, suppose we have a charge. We know that a positive charge is going to have electric field lines that flow away from it. And what we're really going to do is we're just going to draw an enclosed box around this charge and pretty much count how many electric field lines are going to penetrate this box, how many are going through there. Since I drew a positive charge, I'm going to define outward flow from my box to be positive flux. And really, if you think about it, suppose I added another charge inside my box, as they have right here, and I count the electric field lines, it's going to that are punching through my box, it's really going to double. It's going to be a positive outward flux that's double what it was for one charge. For a negative charge, we know that the field lines are going to always point towards a negative charge, and so we're going to have a inward flux that's going to be a negative flux, and same type of concept. If you double the amount of negative charge inside of the box, you're going to double the field lines, you're going to double the flux, the flow. So suppose we drew our box, and that box, we had zero net flux in that box. How is that possible? Well, there's going to be three ways that that's going to be possible to get zero net flux. First, if there's no electric field, obviously you try to count up all the electric field lines going through the box, it's going to be zero. So there's going to be no net charge inside of the box. Another way to get zero net flux is to have a positive charge and a negative charge inside your box, and so the positive charge has all the electric field lines going out of the box, the negative charge has all the field lines going into the box, and positive is going to be out, negative is going to be inwards, and there's going to be zero net flux through this box as well. Q net in this case is going to be positive charge and then negative charge, so it's going to be zero net charge inside of the box is going to generate zero net flux. And another way to do it is to say we have a uniformly charged sheet that's putting off an electric field. It's going to have positive inward flow, it's going to have negative outward flow, and the flux in this case is going to be zero. Also, there is no net charge inside the box. So the only way to get zero net flux is to have no net charge inside of a box. Very important concept. So what's going to affect the flux through a box? Well, we know that it's going to depend on the charge that's inside of it. If we have zero net charge, there's going to be zero net flux. What we can do is we can write the flux, that's going to be the Greek symbol phi, kind of an I with a circle through it, is going to depend on the electric field that's flowing out of our box, as well as the surface area of the box. So in the simplest possible case, just electric field multiplied by area. So here we have our simple point charge, and it's got some electric field associated with it that's flowing out of the surface area of that box, so we have some flux. If we double the charge inside of that guy, that's going to double the strength of the electric field, and so it's going to have a much larger flux, kind of like if we had 2 point charges in there. We counted all the electric field lines. However, if we double the dimensions of the box, you can kind of see that the magnitude of the electric field has gotten smaller. It's going to die off like 1 over r squared. So the electric field has gone down, but the area of the box has gone up. And it turns out that they're going to balance each other out, such that the net flux is going to be the same as in the first case right over here. Important takeaway from this slide is that the size of the box that you draw is not going to affect the flux. Something to kind of think about is, suppose we have a uniform electric field and then just a single sheet with area A right here. We say, well, how much flux am I going to have? Again, the flux, I said in the easiest possible case, is going to be equal to the electric field multiplied by the area. However, suppose I tilt my sheet just a little bit, such that now it's pointing up in this direction and we're missing these electric field lines right down here. We're going to have less flux through the box. Worst possible case scenario is as I rotate it 90 degrees such that it's parallel with the electric field, and no electric field lines are going to go through my sheet, and so my flux is going to be equal to 0. So it turns out that this is not valid all the time. There's going to be a dot product involved. Just a reminder, we're going to say that the flux is going to be the electric field dotted with the area vector, and as a reminder, that's going to be the magnitude of the electric field multiplied by the magnitude of the area multiplied by the cosine of the angle phi between them. The area vector is the area is going to have a normal vector associated with it that's going to be perpendicular to the surface area kind of shown here. That's what this little area A is right there. And occasionally you'll see the area being written, the area vector being written as the area multiplied by some n hat, which is going to be just some normal vector to the surface. So kind of you can see here, this cosine of phi is going to account for there being less flux right here as opposed into the 90 degree case, and here cosine of phi, cosine of 90 is going to be 0. Just a quick little calculation. Here we have a uniform electric field, and we know that it's going to be 2 times 10 to the third newtons per coulomb. Asked to figure out what the flux is for this disk. Flux is going to be the electric field dotted with the area, or the magnitude of the electric field, magnitude of the area, cosine of the angle in between them. Here the disk is off at a 30 degree angle, so that means the A is going to be at a 30 degree angle from the electric field. And so simply we're going to write the flux is going to be the electric field 2 times 10 to the third newtons per coulomb. The area is going to be the area of a disk, pi r squared, so pi times 0.1 squared. And then cosine of 30, and we're going to get 54 newtons per coulomb meters squared, newtons per coulomb from the electric field, meters squared from the area. Something to think about is, suppose that we had the same type of scenario where we had some disk and we had some electric field, but now the electric field was not uniform. Suppose it got smaller and smaller and smaller. Then what we have to do is we have to say, well, I'm just going to look at this tiny little area right there, dA. So I'm going to have some tiny little amount of flux going through that guy that's going to be equal to the electric field at dA dotted with dA. And really I just need to add all of these tiny little guys up, so I'm going to do an integral. So in general, the most general possible way we could write the flux is going to be equal to the integral of the electric field dotted with dA. Both these guys are vectors. Another example worth just mentioning briefly is going to be 22.2. Here we have a cube in a uniform electric field. So really we can say what's the electric field, or what's the flux going to be equal to. Well, if we kind of look at it here, we can see through this surface there's going to be no flux, through the bottom surface there's going to be no flux, and through surfaces 3 and 4 there's going to be no flux. So really the flux is going to be equal to the electric field going in through this surface right here. So the electric field multiplied by the area of that surface, and then all of the electric field is going to be leaving the other side, so it's going to be a minus electric field multiplied by that surface area. This is a cube, and so the flux is going to be equal to 0. Same type of thing if we rotate the box a little bit. The math gets a little bit messy. You can follow what the book does. The flux is going to be 0. Lastly, let's take a look at example 22.3. We're going to say, well, let's take a look at the flux through a sphere, electric field being the interval of the electric field dotted with all those little dA vectors. We're adding up all of these little tiny components here. These dA vectors, they're going to be in the r hat direction. The electric field is also going to be in the r hat, in the radial direction. So it turns out that for a sphere, I can simply write that the flux is going to be equal to the electric field multiplied by the area of a sphere, which is going to be equal to kq divided by r squared. Area of a sphere is going to be 4 pi r squared, and these r squareds are going to actually cancel each other out. Another way to write k, I don't do it very often, is going to be 1 divided by 4 pi epsilon naught, the permeability of free space. So we can now write the flux is going to be equal to 1 divided by 4 pi epsilon naught multiplied by q multiplied by 4 pi. And what you can kind of see is the 4 pi's are going to go away, so the flux through a sphere is simply going to be equal to q divided by the permeability of free space epsilon naught. You're going to start seeing that a lot in the next couple of slides. So now we've arrived at the most important concept of the lecture, Gauss's law. What we're really going to be doing is we're going to be relating charge and electric field, only we're not doing it with Coulomb's law. It's equivalent to Coulomb's law, but it's an alternative to it. So this is the fella right here. I'm not going to butcher his first name, but his last name is Gauss, and he's the one that came up with the law. You might want to think of him as a trickery little devil. So what Gauss did was he started looking at electric field lines and areas. First, let's just start by talking about a sphere. Now here we have already shown that the flux from a sphere is going to be the charge that's inside of it divided by epsilon naught. Now if we say that was my sphere right here, some radius r, some dA right there. Now if we double that radius, essentially we're looking at an area that's 4 times dA. However, the electric field has gone down also like r squared, so it's going to be 1/4 of what it was. And so the flux for the larger sphere is going to be the same as the flux of the smaller sphere, q divided by epsilon naught. So now let's take it a step further. Here we're going to have the same thing we had before. We're going to have a positive charge enclosed by a sphere, and we've already said that the flux on that guy is going to be equal to the charge enclosed divided by the permeability of free space. And now we're going to surround this guy by another really funky shape. Now it turns out that the flux is going to be the same. It's going to be the charge enclosed divided by the epsilon naught. Now, the book kind of shows you right here that it may be a pain in the behind to calculate what this E dotted with dA is, but really it doesn't matter because we can kind of bend any weird shaped object back into a sphere, and the flux is going to depend only on the charge that's enclosed. Positive and negative flux, positive and negative charges. If we write the flux is going to be equal to the charge divided by the enclosed divided by the permeability of free space, that's going to be positive. If the charge enclosed is going to be negative, the flow is going to be into the sphere, and so the flux is going to be negative, as I'm kind of showing right here for a positive charge and for a negative charge. Positive charge, positive flux, negative charge, negative flux. So what Gauss's law is going to boil down to is we're going to relate the flux. This is going to be the electric flux. It has a subscript E that I've been conveniently leaving off. Is going to be equal to the integral of the electric field dotted with the dA. Both those guys are vectors. We typically also write this with a circle there. That is to remind us we need to integrate over the complete surface area of the surface that we're using. That is going to be equal to the charge that is enclosed by the surface that we're drawing divided by the permeability of free space. And the surfaces that we're drawing are going to have a special name. They're going to be called Gaussian surfaces. The real power of this guy is, suppose I have a charge distribution and I want to know the electric field. I can choose my symmetry such that I can go from a charge distribution to calculating what an electric field is, or if I know what my electric field is, I can go the other way and figure out what my distribution of charge is. Now let's just kind of talk about this in terms of flux for just 1 second right here. Suppose we have a negative charge over here and a positive charge over here. We can draw several different surfaces and calculate what the flux is. If we look at surface number A here, we can figure out what the flux is. That's simply going to be equal to the charge that's enclosed divided by epsilon naught, so it's going to be positive Q. If we look at surface number B, so I'm going to say that's part A, the flux in B is simply going to be the negative charge divided by the permeability of free space. If we consider C, the flux inside of C is going to be the charge enclosed divided by epsilon naught. The charge enclosed, that's the net charge enclosed. That's going to be a positive charge and a negative charge. That flux is going to be 0. Similarly, if I look at, so that's going to be surface C. Similarly, the flux in surface D, is there any charge enclosed? No, the flux is going to be 0.